Hello everyone, welcome back, and in today's video we'll cover some mechanics problems. So this is the first problem of the day. So it looks pretty easy, but the problem does require a decent bit of analysis to come to the answer to. So I really like this problem, so let's discuss what exactly the problem says. So we have a small bob that can slide downwards from point A to B along either of the two different curved surfaces as shown in the figure. So these possible trajectories are circular arcs in vertical plane. They lie symmetrically about this line AB. During the motion, the bob does not leave contact with the surface. Okay, so these are the two possible trajectories that they're talking about. Beads are left at point A, and then they're going to slide along this path and reach point B. So in the first option, they're asking if friction is neglected everywhere, bob will take a smaller time through path 1. So we have to figure out which bead reaches a point B quicker. And in option C and option D, we have to figure out who will have a smaller speed when reaching B if friction is considered. So let's begin with the analysis. Okay guys, so I hope you have given it a try, and now, so first let's talk about situation 1 when there is no friction anywhere. Okay, so the fundamental difference between path 1 and path 2 is the accelerations, right? So G vector acts vertically downwards. So the closer the path is to the vertical, greater its acceleration. So which means the acceleration of the bead along the path 2 initially will be greater. So initially the bead will accelerate quick in comparison to bead number 1. So before we begin, we can directly answer option C pretty easily. So in the option C, they are saying if friction is neglected, then the bob will reach point B with the same speed along both the paths. So this is essentially a problem on conservation of energy. As we can see, the change in potential energy between the point A and B is the same for both of the bobs. So the work done by the gravity will be the same for both of them. And as there is no friction, they both will have the same velocity when they reach the point B. So option C, and therefore option C is correct. Okay guys, so now we have to figure out the time. And in order to figure out the time, we have to figure out who is faster. Okay guys, so now let's say I take a small segment over here. Let's say AB. So let's say the bead starts from A and reaches B. Similarly, I'm going to take a symmetrical element on the other branch, and let's call it A dash, B dash. They're both equal in length. Okay. Okay, so first of all, why is this symmetric? Because in the question, it is given that both the paths are symmetric about this line AB. So you can consider this line AB as a mirror, and A dash, B dash is just the mirror image of AB. Let's say the bead reaches the point A dash with a velocity of V1, and the bead reaches the point B with a velocity of V2. Okay, so now we'll use the energy conservation argument. We can clearly see from the diagram that point A is lower than point A dash, which means work done by gravity for the bead along path 2 is greater, meaning V2 will be greater than V1. This is pretty easy. It's because the point A is below the point A dash. Okay, so its potential energy decreased more, so its kinetic energy will be greater. Okay, so now we figured out if I consider any two symmetrical paths on path 1 and path 2, then the speed with which bead 2 covers that path is greater than the speed with which bead 1 covers that path. And this argument you can prove for any symmetrical path, right? You can take any symmetrical path and speed of bead 2 will clearly be greater than the speed of bead 1. And this is true for all paths. Well, if bead 2 covers each of these small paths with a velocity greater, then it must take lesser time. So, and therefore we can say bead 2 takes less time to cover the distance. So the bob will take a smaller time to cover path 2 as compared to path 1. Okay, so option B is correct. So now we have to talk about friction. Okay, so firstly, friction at each particular point will depend on the normal at that point, right? So, and we can clearly see that the normal reaction is varying with point to point. So let's say I take any random path, something like this, okay? And let's just assume the slope here to be constant. Like clearly slope is varying along the path, but let's assume a small path where the slope is actually constant. So now we can break down the gravity into components. So let's say one component of the weight is mg parallel and one component of the weight is mg perpendicular. Okay, so in this element, the normal reaction will be in this direction. Let's call it N1. Friction will be tangential to the path and its magnitude will be mu N1. So this is the FVD of the bead when it reaches this particular point over here. Okay, so we have to compare the final velocities. So clearly we'll take the path of the work energy theorem. So which means we have to essentially compare the work done by friction. So the components of the weight along and perpendicular to the point, it depends on the slope at that particular point, right? So if I zoom in this element, it's going to look something like this. And let's say this angle, the tangent makes with the path is, let's say, theta. So G parallel, we know it's going to be G sine theta. And this is going to be G cos theta. So the components of gravity essentially depends on the slope. That's what I'm trying to say. So if I want to compare it to a corresponding path which is along the second path, then I have to do something. So let's say I join point A to B, and let's say this is the midpoint of the line AB. So the element that has the same slope as this particular point over here is a point that is symmetrical with respect to the midpoint of this line AB, which is going to be this particular point over here. Okay, so if you want to visualize this a bit more, then you can consider the element to be horizontal, something like this. So the element that has the same slope as this particular point is this particular point over here, and this point is symmetrical with respect to the center. So now let's draw the FBD at this particular point. So here the normal will be again in this direction. Let's call it, okay, actually let's draw it over here. It's going to be N2, let's say. And the friction will be again tangential to the path. Its magnitude is going to be mu N2. And the components of gravity remain the same. Mg parallel along the slope and Mg perpendicular to the slope. Okay, so now let's write the force balance equation in the normal direction, bead along path 1. Okay, which is this bead over here. So again, it's given that these two paths are along a circle, right? So the center of the circle for path 1 actually lies on this side. So if I want to write the equation, it will be the net force towards the center of the circle, which is mg perpendicular minus n1 equal to the net centripetal acceleration, which is going to be m v1 square divided by r. And I assume the radius of the curvature of this path to be r. Okay. So now the thing is, if I similarly write the equation for the bead in path 2, here you can see that the center of curvature lies on the upper side. It lies over here. So here it's going to be n2 minus mg perpendicular equal to m v2 square by r. And here obviously the speeds are going to be different, guys. From here n1 is going to be mg minus mv square by r, whereas n2 is going to be mg plus mv square by r. So comparing these two equations, we can easily see that n2 is clearly greater than n1 for all such symmetrical paths. It means that if n2 is greater than n1, then that means the friction force acting on the bead at 2 is greater than F1. Now, if friction force is greater for this path along bead 2, more of its mechanical energy is destroyed. So the work done by friction along path 2 is going to be greater than the work done by friction along path 1, which means the speed with which bead 2 reaches point B is going to be less than the speed with which bead along path 1 reaches B. So if friction is significant along both the paths, then the bob will reach B with a smaller speed if it follows path 2. So option D is also correct. So the answer to this question was option B, C and D. Okay. So now let's move on to the next question. So in the next problem, we have a motor that is installed at the top of a pole rigidly fixed on a platform. A light rod of length 1 meter is rigidly attached to the motor shaft at its one end, and at the other a small ball of mass m is attached. The rod can be rotated in a vertical plane with the help of the motor. Total mass of the platform, the pole and the motor is 4 times that of the mass of the ball. The motor rotates the rod at a constant angular velocity. The platform is placed on a horizontal surface where coefficient of friction is 1 by root 3. So we have to figure out the minimum angular velocity with which the platform will start sliding. So essentially this rod over here is rotating with some angular velocity, and so the pole, the motor and the platform together have a mass of 4m. So we need to figure out the minimum omega for which this platform, this structure will start sliding. Okay, meaning the friction here will become limiting. Okay, so let's discuss the problem. Okay, so before we begin with this problem, we'll need a basic result which we derive in Newton's laws of motion, and the result is the minimum force that we need to pull a mass m kept on a rough ground. Now you can obviously solve this with calculus. We can quickly prove this by drawing a vector triangle. So for that we have to analyze the forces on this mass m. So first we have the external force F, and then we have the weight of the mass mg. Then we have normal reaction and the friction force. So and guys, the friction force when the body is just about to slip is going to be mu n, right? Or limiting. So what I'm going to do is I'm going to call the resultant of n and mu n as r. And the thing is, this angle, I'm going to take it as alpha. And from the vector triangle, we can see that tan alpha is nothing but mu. So now we have 3 forces that we have to put in one vector triangle. We need the minimum force F required to just move the mass. So F vector plus mg vector plus r vector, these 3 forces together should add up to 0 if we want to calculate the minimum force required to move the body. So, and if we increase F even a little bit beyond that F minimum, we should be able to move the block. Okay. So what I'm going to do is draw f vector, mg vector and r vector now. So mg vector is the easiest vector to draw because it's a constant vector and its direction is in the vertical direction. So let's just mark it real quick. With f vector and r vector, there is a problem because f vector is clearly variable, right? We don't really know exactly the magnitude. And the thing is, r vector, if you guys observe, n actually depends on f. If you write sigma fy equal to 0, you can see that n actually depends on f. So even r vector is variable. But we know one thing for certain. When the block is about to slip, this r vector will make the angle alpha. Why? Because tan alpha is always equal to mu when it is about to slip. So we can actually take advantage of this. So meaning the direction of r vector will be the same always. So we can't really say much about the magnitude, but we can certainly figure out its direction. So the direction will be along the dotted lines that I just drew, and its angle will be alpha with the vertical. Let's say this was the r vector. Okay. In this case, if I want to complete the vector triangle, this will be f vector. And let's say if we take this point, this will be the f vector. So if I have to connect this point to some point on the dotted line, the minimum length will occur when this line is perpendicular to the dotted line. So the length of this particular side will give us the minimum force that we need. And this angle, we know it is alpha. So from the vector triangle, we can easily see f minimum is mg sine alpha. Now tan alpha is mu. So sine alpha is going to be mu mg divided by square root of 1 plus mu squared, which most of you guys might already know. But the more important thing I wanted to point out is the angle f vector makes with the horizontal. This angle is 90 minus alpha, meaning this angle is going to be alpha. Angle the f vector makes with the horizontal is also alpha. Okay, and again alpha is a tan inverse of mu. So the answer to this problem is I have to apply mu mg divided by root 1 plus mu squared at an angle of tan inverse of mu if I want to move the block. So now let's move on to our question. Okay, so in the given problem, they gave us that the mass of this much part is actually 4m. Right? Rod was attached to this particular point over here at the top. So the minimum force that I have to apply to move this structure is going to be, let's say it is F. I can directly write its magnitude as mu mg, and here m is 4m into g divided by square root of 1 plus mu squared. And it needs to be applied at an angle of alpha, and alpha again it is tan inverse of mu. And mu is given to be 1 by root 3 in this case. So this comes out to be 30 degrees. So now we know the magnitude and direction of f. Now I can draw the FBD of the ball. So the ball was connected to the rod. Okay, and the rod makes an angle of 30 degrees with the horizontal. Now guys, as this rod is given to be a light rod, everywhere along its length, the tensile force is going to be the same. So we know at this particular edge, the rod is pulling on the structure with the force F. So everywhere along the rod, the tensile force is F. So the rod will pull on the ball with the same force F. And there is also the ball's weight acting downwards. And this angle is 60 degrees. And the acceleration of the ball is omega square r. Now we can apply force balance along the radius. So we can say F plus mg by 2 is equal to m omega square r. So from here we can put the value of F into this equation. And after solving these two equations, you'll get the value of omega as 5 radians per second. Okay, so now let's move on to the next question. This problem is to revise the topic buoyancy a little bit. So we have a small ball that has a density of rho, and it is held at a point A over here in a cubical container of side length L filled with an ideal liquid of 4 rho as shown in the figure. So now if the container starts accelerating in the horizontal direction with A and the ball is released at point A simultaneously, then we have to answer these problems. So first let's try to draw the FBD of the ball. Okay guys, so first let's say we have a container filled with water and it's accelerating in some arbitrary direction with an acceleration of A. And let's say the fluid relative to the container, it remains at rest. Meaning for a guy standing on the ground, he will just see a container with fluid moving with an acceleration A. He will not see the fluid moving relative to the container. Okay, if I take a small volume dV of the fluid, even this fluid is accelerating with the same acceleration of A. So let's take a small patch of the fluid element, and we can now say the acceleration of this patch of fluid is also. Now if this fluid element is accelerating in this direction, there must be some force acting on this fluid element by the surrounding fluid, right? And that is the buoyancy force. So if I draw the FBD of this element, let's say the buoyancy force acts on this element in some arbitrary direction, and let's call it as FB vector. And this element also has the weight of the element acting, which let's just call as V rho G. Okay, let's take the volume as V and the density of the fluid as rho. And its acceleration is A. So now I can write the F equal to ma equation. So I can say buoyancy plus its weight equals the mass of the element, which is V rho times the acceleration. And from here we can easily see that the buoyancy comes out to be rho V times A vector minus G vector. So basically, if I want to redraw its FBD, then and if I want to write down its buoyancy force directly, so firstly, so one component is rho v a vector, which means that will be in the direction of a vector, and its magnitude is rho v a, and one component is minus rho v g, meaning its direction is opposite to g vector, so it will be in the vertically upward direction, rho v g. And as you can see, this rho v g cancels out with the weight, and therefore the object does not have any vertical acceleration, and this rho v a will provide an acceleration a similar to the acceleration of the container. So now we can analyze the given problem. The density of the fluid is 4 rho and the object's density is rho. So firstly, we have the weight of the object acting downwards, which is rho vg. And then we have, as I said earlier, there is a component of buoyancy in the direction of acceleration whose magnitude is 4 rho, which is the density of the fluid, volume into A. And then we have a buoyancy component, which is going to be 4 rho vg. So this is the FBD of the ball. So now you guys may have a doubt, why didn't I take normal reaction into account? So, and that'll be clear if you guys write down the horizontal acceleration of the ball. So if you see, the horizontal force is 4 rho VA, and if you divide it with the mass of the ball, you'll get the answer as 4A. So the ball's acceleration in the horizontal direction relative to ground frame is 4A towards the right, and the ball is accelerating with an acceleration of A, meaning the ball actually accelerates faster, and therefore there won't be any normal reaction. And the acceleration in the vertical direction is going to be 3g, right? And that you can, how did I get that? 4 rho vg minus rho vg is 3 rho vg divided by rho v, and you'll get 3g. Distance was given to us as L by 2. So this point was point A, this point was point Q. So we need to figure out the time in which it would reach point Q. So we can easily write S is equal to ut plus half at square in the y direction. So it will be, the displacement is L by 2. It will be equal to half acceleration into t squared. The time turns out to be square root of L by 3g. In a time of square root of L by 3g, the ball will reach the top of the container. And the other question was, for the ball to hit the top of the container at the end Q, what is the value of A? And this problem we have to do relative to the container, right? So the ground frame acceleration of the ball is 4A, meaning relative to container it will be 4A minus A, which is going to be 3A. So now we can use Sx equal to half ax t squared, and relative to container the ball has to cover a distance of L to reach the point Q. Sx is going to be L, and this is equal to half ax into t squared, and t is square root of L by 3g. And from here we can see that the acceleration A has to be equal to 2g. The answer to this question is option B and option. Okay, so in this question we have a plank that is moving along a smooth surface with a constant speed of v. A block of mass m is gently placed on it. Initially the block slips and then acquires a constant speed v, same as the plank. Throughout the period, a horizontal force is applied on the plank to keep its speed constant. So this guy's speed is constant always, whereas the mass m, it slips on the plank and finally attains the velocity of the plank. So we have to figure out the work done by the external force, and we have to figure out the heat developed due to friction. Okay, so initially when the block is slipping, we know that the friction is actually kinetic in nature, and whenever we have to talk about the work done by kinetic friction in such combined mass problems, the work done by the kinetic friction, it comes out to be frame independent. Okay, so I'm not going to prove this result right now. I'll link a video in which I have actually done the proof of it. So when we say the work done is frame independent, what we mean by that is, even if I solve it taking the frame of reference as the plank or the frame of reference as ground, I would get the same work for the work done by kinetic friction. Okay, we know work in general is frame dependent, but in the case of kinetic friction it turns out to be frame independent. And we also know that the work done by all the non-conservative forces, which in this case is kinetic friction, equal to the change in the mechanical energy of the system. So basically the dissipative work done by kinetic friction is lost to the surroundings in the form of heat. As we know that this kinetic friction work is frame independent, we'll just solve it in the frame of the moving plank. So guys, the plank's velocity is constant. Okay, so relative to the plank, the mass will initially have a velocity of capital V towards the right, and then it will start slipping on the plank, and finally it will come to rest. So the initial velocity of the block is V, and the final velocity will be 0 in the relative frame. Now we know that when the block is actually slipping on the plank, throughout the friction force will be mu mg, right? So it means that the deceleration of the block is mu g. So now we can write v square minus u square equal to 2a times the displacement. So the relative displacement of the block on the plank is actually v square by 2 mu g. Now we can easily determine the work done by kinetic friction. It will be the force, which is, it will be F dot S, and here force and displacement are opposite to each other. So the work done by kinetic friction is negative, as it should be. So this is going to be minus mu mg times v square by 2 mu g and this turns out to be minus mv square by, and this would be the same even in ground frame. And this is also the decrease in mechanical energy of the system, or we can also say it is the heat lost to the surroundings. So in the option C, they're saying what is the heat developed due to friction, and we figured out it is half mv squared. So C option is correct. So now we have to figure out the work done by the external force. So we can see that the friction force on the block is actually towards the left and its magnitude is mu mg. So by Newton's third law, a force of mu mg will act on the plank as well, right? So the external agent's force will be towards the left, and we need to figure out the work done by F. So initially the block's velocity was 0 and the plank's velocity was v, and finally they both have a combined velocity of v. So now we can apply work energy theorem for this combined system. So the work done by all the forces, which includes the external force F and the internal forces. So internally we know that kinetic friction does a work of minus mv square by 2. So let's just write it over here. So this is the work done by kinetic friction. This would be equal to the change in kinetic energy of the system. So the kinetic energy of the plank did not change, but the speed of the block increased by a value of v. So the change in kinetic energy of the system is half mv squared. So from here we can figure out the work that the external agent has to do is mv square, which corresponds to option. So that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.